Okay, there are a number of equations that you need to use and apply, and it's going to be a bit strange to see lots of mathematical equations now. However, the solution to the simple harmonic function is basically a mathematical one, so we would have to just get used to using these equations. Now these are the equations. X is, of course, the displacement. X naught is the maximum displacement, or the amplitude. Omega t is basically, omega is the angular speed, and remember, speed times time gives the distance. So omega t will give you the angle that is turned. V naught gives the maximum velocity, and the v gives the velocity at any particular time. Now, well, there are two equations here, both representing x. Now, why is one cosine omega t and one sine omega t? And it really depends on where you start the timing. If you start the timing at x is equal to x naught, in other words, we use cosine omega t. For example, when you're pushing a swing, you start and you release the swing when it's the maximum displacement. If, however, if you start when from the equilibrium position, from the vertical position, let's say, then you use this equation, which is a little bit cleaner to use. So this is when it starts, when x is equal to 0, when it starts at the equilibrium position. So you'd have to listen carefully to the question on how it starts to know whether you use the cosine or sine omega t. Now this equation here can be simplified to this: x naught squared minus x squared. Basically, the maximum velocity is when it's going through the equilibrium position. In other words, x naught will be equal to 0, so it's going to be basically x squared square rooted. So it's the maximum velocity is equal to omega x max. Another way of putting it is that the velocity that goes around in a circle is equal to omega r, because r is basically the amplitude, in other words, x max, x naught. Now we can use circular motion and the equations of circular motion to basically analyze simple harmonic motion. Notice this vertical oscillator here. It can be represented by this line going around in a circle. Yeah. And now we will look at a graphic which will kind of put that in another light. Here we have an example of simple harmonic motion. We have an oscillating spring which is oscillating in the vertical direction. Now the position of the spring varies with time, and this can be represented with the graph on the right. And if I stop this, if we start here, notice that it's in the equilibrium position at time is equal to 0. The next moment it moves upwards slightly, and this shows the position at a time t. Each step goes a little bit further until it reaches the high point, which is the amplitude of the oscillation after a quarter of an oscillation. We keep on with the steps. At this point, it's just gone past the equilibrium position again, and this is half a time period later. So the position of the mass can be represented by a sine curve starting at the origin. Furthermore, this can also be represented by a graphic to show circular motion. If we start in the 0 position here, as this moves up, this arm will sweep round in a circle. So if I show the step here, after 1/4 of an oscillation, there, this has travelled by 90 degrees, or pi by 2 radians. Carry on to be a complete half circle. This is now pi radians. We're going back to the equilibrium position again, and it's half a time period, and so on. If we see it playing like this, we can see that this circular motion here can be a graphic representation of the position of the mass with time. And this can also be shown as a sinusoidal curve. So basically, the function, simple harmonic motion, can be represented by a sine curve, or it could be a cosine curve if it starts at the highest point here. But we'll start with the simplest case, which is when t is equal to 0, the displacement is equal to 0. So, we know that simple harmonic motion can be shown by the displacement in the vertical direction of x0 can be shown by a vector moving around in a circle. And the vector, this rotating vector, has travelled an angle of theta or omega t. We're starting at the 0 point here, when t is equal to 0, x0 is equal to the starting point. So this is going to be 0 here. As this sweeps round, then this will move upward. So we get a sinusoidal case. This is a sine, so it's going to be x is equal to x0 sine omega t. Remember that the distance is equal to the speed times time. So this is your omega, which is the angular speed times time, gives you the distance, or the angular distance, or in other words, the angle. Remember, omega is equal to 2 pi f, so the angle is equal to 2 pi f times by t. Now let's take this example here. X is equal to x0 sine omega t if and only if time starts when x is equal to 0. In other words, the equilibrium position. So, and if it starts at x is equal to x0, in other words, at the maximum amplitude, then it's going to be x is equal to x0 cosine omega t. For example, what is the displacement of a swing 0.4 seconds after it was released from x0, in other words, from the maximum? The frequency is 0.5, the amplitude is 2 meters. Find the acceleration at that point and the velocity. So to find the displacement, which equation are we going to use? The swing is released from its maximum position, so in other words, we use this equation to find the displacement. What is x0? This is the amplitude, which is known as 2. Cosine omega t. What is omega? Well, we know the frequency, so we can find out 2 pi f. And we know time is equal after 0.4 seconds. So then you can find it just by applying that. The acceleration is what we use with simple harmonic motion. A is equal to minus omega squared x. We know what x is. We find the displacement here, of course. Find the velocity. Well, we use the other equation where v is equal to v0 cosine omega t. Or in this case, v is equal to v0 sine omega t. So the first one, we find that x is equal to x0 cosine omega t, 2 cosine 2 pi f, frequency is 0.5 times by t, 0.4. The acceleration is minus omega squared x, we know what x is. And the velocity, we can use this equation, or at that point, or we use one of the velocity equations. For those who have done calculus, the relationship between speed and distance and time can be represented this way. X is equal to x0 sine omega t. If we differentiate with respect to t, x divided by t, how much is the distance changing with respect to time, which is the velocity? We end up with dx by dt. If we differentiate that, we end up with, we have to multiply by omega times by x0 cosine omega t, which is what we have here. So the velocity is equal to omega x0 cosine omega t. But when omega t is equal to pi divided by 2, which is basically a quarter of a term, cosine omega t is going to be equal to 1. So the maximum velocity is equal to omega x0. Or we could say the velocity, maximum velocity is equal to omega r, because that's the size of the amplitude, or the size of the radius of the circle that we use to represent simple harmonic motion. This is the max velocity, and this is the maximum displacement, or the radius of the circle. If we differentiate again with respect to t, we have d2x by dt squared, so we're differentiating this one again. We end up with multiplying, taking out this factor of omega again, so it's omega squared. Of course, we differentiate cosine, we end up with a negative sine omega t, which is all well and good. It's starting to look a bit complicated, but it really isn't, because we know x naught sine omega t is also equal to x. So we say omega squared x. So d2x by dt squared is equal to negative omega squared x. But what is the rate of change of velocity with time? We know that's the acceleration. So the acceleration is equal to minus omega squared x, which is the proof of simple harmonic motion. This is the basic equation that governs simple harmonic equation. A is equal to minus omega squared x. This is if you're happy with calculus.